You've seen them, right? These massive, graceful giants spinning on the horizon. They look so simple, almost like giant pinwheels. But what's actually going on inside is a whole different story. It's a mix of some brilliant physics, incredible engineering, and a surprising, totally unbreakable law that limits just how much power we can ever pull from the wind. So, let's get into it.
Okay, let's just start with a puzzle. If you want to get all the energy out of the wind, why not just build a turbine that completely stops it? Like a giant wall that catches every single bit of motion. It sounds totally logical, but it's actually completely wrong. And understanding why is the key to, well, everything.
The answer is this number right here, 59.3%. And that isn't some engineering target we're trying to hit. It is a hard limit set by the laws of physics. No wind turbine, no matter how futuristic or advanced, can ever capture more than this percentage of the wind's energy. It's called the Betz limit, and it literally rules over every single turbine ever made.
So what is this invisible barrier? Well, back in 1919, a German physicist, Albert Betz, he's the one who figured it out. He wasn't looking at gears or materials. No, he was studying the air itself. And what he found was the central paradox of wind power.
Here's the big idea. Think about it. If a turbine was just a solid wall, the wind would have nowhere to go. It would just sort of pile up in front and flow right around it. And if no air passes through, you get zero power. So to generate power, you have to let the air pass through, which means you can't possibly take all of its energy. Betz did the math and found the sweet spot. Slow the wind down to exactly 1/3 of its original speed. And boom, you hit that magic number, 59.3% efficiency.
And this challenge isn't exactly new. We've been using wind for over 2,000 years, from ancient windmills in Persia to the very first electricity-generating turbine back in 1888. But it was really after Betz defined that limit in 1919, and especially after the 1973 oil crisis kicked research into high gear, that the modern race to get as close to 59.3% as possible really took off.
Okay, so if you can't break the limit, how do you engineer the absolute best machine to work within it? Well, the answer lies in a design that's way less like an old-fashioned windmill and a lot more like an airplane wing standing straight up.
And this right here is the absolute key. The secret isn't just brute force, it's all about aerodynamics. See, old windmills use drag. The wind literally just pushed them. But modern turbines? They use a principle that's way, way more powerful. They use lift. It works exactly like an airplane wing. Each turbine blade is a special shape called an airfoil. It's curved, so air has to travel faster over the top surface. And faster air means lower pressure. That pressure difference between the top and the bottom creates a force, lift, that actually pulls the blade forward, making it spin. It's so much more efficient than just being pushed around by the wind. Now, all the magic happens up in that pod at the top, which is called the nacelle. The blades turn the rotor pretty slowly, but with a massive amount of torque. Inside, a gearbox kicks that rotation into high gear, sometimes by a factor of 100, to spin a generator really, really fast. And that's what finally turns that motion into electricity. So that's the basic idea. But not all turbines look the same. Engineers have come up with two totally different ways to catch the wind, and it all depends on which way the main rotor is pointing. On one hand, you have the horizontal axis wind turbine, or HAWT for short. This is the classic design you see everywhere. It makes up something like 90% of all turbines. They are super efficient, but they have to be pointed right into the wind. Then you've got the vertical axis, or VAWT. They're not as common, but they have one killer advantage. They can grab wind from any direction, which makes them perfect for certain spots. HAWTs are really the champions of big-time power generation. You find them in these huge farms, either offshore or out in the countryside, where there's nothing but wide open space and steady, predictable wind. But VAWTs, they are the specialist. Because they're omnidirectional and usually quieter, they're just ideal for the messy, chaotic wind you get in cities. Plus, you can put the heavy generator and gearbox right on the ground, which makes maintenance way easier. So we've talked physics and engineering, but what about the bottom line? What does it actually cost to get electricity from these things? Well, the industry has a way to measure this called the levelized cost of energy, or LCOE. So, looking at 2024 data, the costs are really different depending on where you build. A land-based turbine can make electricity for about $42 per megawatt hour. But if you take that turbine and put it offshore on a fixed foundation, the cost jumps to $117. And for the really new floating offshore designs, it's even higher at $181. That massive price hike is really the cost of building and maintaining these things out in the harsh, deep ocean.
But where does that $42 for the onshore turbine even come from? It's not just about buying the turbine itself. This chart here gives us a really fantastic breakdown of all the costs over its entire life.
Okay, so the turbine itself, the tower, the blades, the nacelle, that's the biggest single piece, at about 42%. But check this out. This number might be the most surprising. A full 25%, a whole quarter of the lifetime cost, is just keeping the thing running. We're talking maintenance, repairs, day in, day out. So yeah, building it is one thing, but operating it is a whole other huge expense.
So, after this whole journey through physics, aerodynamics, and economics, what's the big takeaway? And maybe more importantly, where's all this amazing technology going next? You know, it all comes back to this really basic principle of energy. It doesn't matter if it's water flowing through a dam, or heat moving from hot to cold, or wind blowing across a field. You can only generate power by tapping into a flow. You can't just block it, you have to become a part of it.
When you really think about it, the story of wind power is all about working with nature, not trying to fight it. It's about understanding this fundamental physical limit and then using absolutely brilliant engineering to get as close to that limit as we possibly can, all while trying to make the real-world economics work.
And that brings me to one last really cool thought. For 100 years, the Betz limit has been seen as this absolute, unbreakable wall. But what if it's not? Right now, researchers are playing with designs that use these special funnels to cram more air through the blades, which could theoretically beat the limit for a certain area. Could the turbines of tomorrow look totally different from the ones we see today?
Hey, if you enjoyed this deep dive and you want to understand more about the technologies that are shaping our world, make sure to like this explainer and subscribe to the channel. Thanks for watching.